And then
I want to be by the beach and I want to have a hammock and it should be nice and warm. And I want to drink a fresh coconut.
can I just take the volume of the
Yesterday when we were
you just want to take the audio
Sunday was even more
after the computer so that redirected to my
transfer 12 GB of data. I have to download one server and upload it.
Because if anyone speaks online, it will use my computer. Oh, make sure that this computer is muted. It has no volume as well.
I think that was.
No, but I don't have any USB in USB-A. Oh, it's this one, possibly. Hello. Can people online hear us?
I can hear you there, Eric. Yeah.
Yes.
Okay, and we can hear you from the room system, so that's perfect. Lovely. Thank you. Okay, so it's worked like that. So George, we're not using the room microphone system, so the microphone is in the laptop. Just bear in mind that as you like speak, and maybe like you want to like beam that into that direction.
Okay.
Let me just check how much charge do I have. 72%. I'm gonna just dash upstairs and get the charger just in case, and then we can start. I'll be back in 5 minutes.
See? It's not.
Is there time pressure to get out of the room at 3?
If there's someone who can.
Yeah. I don't think I have an hour's worth of stuff, but I just need to know.
I think we have
Directly out. So we have to be out at 3 or we have to be out at 4? Okay. There's no rush.
I think I just book you now. Just for a few minutes.
That's why it beeps.
That's an obstacle.
No. Yeah.
Just realized something.
Sorry?
I just think I would like to scan my desk.
That is standard.
We're getting an aubergine. I'm like, why the hell are they giving me aubergine? But this is why. That's so dumb.
You were joking when you were like, oh,
No, this just happens. And it's like, I guess my code looks like just one digit away from the aubergine or something.
So they probably looked at you like, you look like you need an aubergine. There's an aubergine. Why do you have an aubergine sticker on your phone?
Because I didn't want to throw it away or something.
You also have an aubergine sticker?
Yeah.
Wait, are we talking about like the fruit, the vegetable, or like an emoticon?
Where are you going?
You know what I meant. So.
I mean, people like kittens and then they put like. Sticker or something.
I'm worried. I love kittens.
It's not titled Growing Networks. I think it was.
I think I changed it.
It's actually very
It was too big. It's just new one.
I was actually I took your like title.
Yeah, I changed it.
Sorry. Sure. Good afternoon, everyone, and welcome to this talk of the network seminar. Today, we're very excited to have the first guest for an in-person talk. And today we will have George Cantwell from the Santa Fe Institute. He's a returner because he did his undergrad here in Oxford, and then he did his PhD at the University of Michigan. And today he's talking about his research in computational complexity networks and statistical mechanics. Perfect. This is yours. Thank you for coming.
Thanks, Eric. Thanks for having me. So I will be talking about growing networks, but I want to start with a very simple question, which is just what is the volume of a triangle, or the area, I should say, of a triangle? So probably without even thinking about it, your brain just automatically fills in. So this is, one unit width and 1 unit height, this is just a half. You would have learned that as a child, and you probably never really thought about it in much detail. In 3 dimensions, you can ask the same thing. So now instead of area or volume, and you can make a 3-dimensional right angle triangle by starting with a right angle triangle, gluing right angle triangles onto the sides, and then folding that out into the third dimension. So this is what that looks like. And this is also something, a formula you probably learned in school, but may have forgotten. It will probably be less deeply embedded. But the volume there is 1/6 times the linear dimensions. This would also just have been given to you, probably without much explanation. Unless you went to school in 4 dimensions, you almost certainly didn't learn the 4-dimensional analog, which is 1/24. And obviously, the mathematical question, what is the general formula in dimensions? From this sequence, there's a good chance you can already guess. You've got 2, 6, and then 24. It's the factorial numbers. And these shapes in high dimensions are called simplices, and they arise quite commonly in statistics. So this formula might just be something you know, 1 over n factorial, but it's instructive to think about why it's true. The one way to prove it is just to take the the definition of what a volume is, and a volume is an integral. And you can work through this. So we can draw some axes on here, and we can define a function, f of xy. Its function is 1 whenever you're inside the triangle and 0 everywhere else. So the definition of area, more or less, is just the integral of this function over R2 over the real plane. That's a thing you can do. It's fairly straightforward. You can do the same thing for any finite n. You could do this integral if you wanted to. You can also come up with an inductive argument to show that this is true for all n. And so this is one way of proving that the volume of a simplex is 1 over n factorial, but it does not really provide any insight into why this is the case. A much nicer argument, in my opinion, is a probabilistic argument. So let's say that we have 2 random variables, x and y, that are
We seem to have lost the sound online. I don't know if that's anything.
Okay, am I good?
Oh, good, thank you.
Okay, great. So when you fold out the two-dimensional triangle into 3 dimensions, well, now you can make the same argument with three random variables. And if you just kind of look at the geometry of this, you can see that instead of corresponding to the region y is less than x, now you're folding out and you're getting z is less than y is less than x. So this region here is just z is less than y is less than x inside the unit cube. With that probabilistic argument, there are six possibilities for the ordering of 3 things. So each one of those is exactly equally likely, 1 in 6 probability. Equivalently, the volume is 1 in 6. In n dimensions, same thought experiment, n random variables, how many different orderings are there, n factorial different orderings. So in n dimensions, the volume is 1 over n factorial. So that is, those shapes are simplices, they're kind of the simplest shape in high dimensions, in some sense. You can ask the more general question, what can we say about other shapes in high dimensions and how can we compute their volumes? And this is a relatively well-studied problem in computer science. Dyer and Fries have this paper. The title doesn't give away the punchline. So here's the punchline, which is computing the volume of a convex polytope with sharp P hard. So that's 2 pieces of important jargon. A convex polytope is a shape with flat sides. Well, a polytope is a shape with flat sides. A convex polytope is one of those things that's convex. So it's ball-like, and the sides are just flat. So this is just defined by a system of linear equations, and there's no little tunnels or there's no funny business going on here. So in some sense, a convex polytope is sort of the next simplest shape in high dimensions. Sharp P hard is a computational complexity class, and it's a little more difficult to explain, but I will run through just now quickly what that actually means. So you've probably heard of P and NP, and in some sense, informally, P is the set of easy problems. So it's the set of formally it's the set of decision problems that can be solved in polynomial time. And polynomial time means that for a problem of size n, you can bound the time it takes to find a solution in some power of n. So in some constant times n to the power k for some constant k. And a decision problem just means it's a yes/no problem. So these are just questions like, is there an x? And you can provably answer, is there an x in some time that's bounded by some power of n. So an example, in an array of n numbers, are any greater than 10? This would be a problem. It's a yes/no question. In that case, it's kind of obvious you can do this in linear time. So if I double the number of numbers, at worst, it doubles the length of the time I have to run my algorithm. And the obvious algorithm is just go through every single number and check, is this one greater than 10? Is this one greater than 10? Is this one greater than 10? So that would be linear time, the linear time problem. Sorting is not a decision problem, but it's a very common thing that you may well have come across different algorithms for sorting around n numbers. The merge sort, heap sort, also quick sort can do this in n log n. And it is also a polynomial time problem because log n grows slower than n. So this, I mean, for a start, you can bound this by n squared. So in some sense, these are the easy problems. Although even that is a little bit of a misnomer. So suppose you have some data analysis, some algorithm, and you test it on a data set with 100 data points, and it takes 1 microsecond. But the data you actually want to analyze is 200 data points, so just twice as big. And you know that your algorithm should converge or quit or whatever in polynomial time. And you just want to get a kind of ballpark figure of how long this will take. So O1 means constant time, so if I double the size, it doesn't take any longer to run. Linear time, ON, if I double the size, it takes twice as long to run, 2 microseconds. N squared is starting to get a little bit more noticeably worse. Now it's 4 times as long. But even if my algorithm is n to the 100, to a theoretical computer scientist, this is an easy problem. But when I double the size of my data, it now goes from 1 microsecond to 3 million times the age of the universe. So although this is technically the set of easy problems, even within P, there are potentially problems that are just like completely intractable. N cubed is probably a more practical limit for sort of moderate sized data. So matrix inversion is n cubed. Well, it doesn't have to be, but the standard algorithms are. And once you get to around 20,000 rows and columns, desktop computers start getting upset, and that's about the limit. And I don't know how big supercomputers can go, but if it's quadratic, then it's getting pretty bad pretty quickly. With big data, n log n is really a much more plausible limit on what you can actually do in practice. If you think about something like you have some algorithm, your Facebook, and it's supposed to analyze every post that people make or store it away in some particular way. If that's growing, even if that's growing as the square of n, then every time someone posts a new thing on Facebook, it's even more expensive than the last one for your computer, for your system to deal with it. So, polynomial problems are said to be easy, but even that is a bit of a misnomer. The reason they're thought of as easy is because basically everything else is much harder. So there's a closely related set to P, which is NP. P is the set of decision problems that can be solved in polynomial time, and NP is the set of decision problems that can be proved or checked in polynomial time when they're in positive instance. So P is definitely a subset of NP. If I can solve the problem in polynomial time, then I can check the problem in polynomial time because I just solve it again. If you give me a solution, I just solve the problem and check it's the right solution. But there is a question that is sort of an open question or an unresolved issue, which is whether P is equal to NP. So that's the question of whether every problem that can be checked in polynomial time can also be solved in polynomial time. And I think the orthodoxy is that that isn't true. And I'm just going to, for the rest of the talk, assume it isn't true, just so I don't have to put a load of conditionals if this, then this. So the picture that you have is you have this oval here, this is NP, and then P is some subset of NP. Beyond that, you have problems that are NP hard. So these are problems that can encode any problem in NP. So the way to think about this informally is basically these are the problems that are as hard as the hardest problems in NP. And I mean, this is again not proven, but it's widely accepted that NP-hard problems need exponential time to solve them. So they cannot be solved in polynomial time, which basically means even n to the 100 would be great. We're in a worse situation than that. We're in a situation where the time it takes these problems to be solved grows exponentially, worse than any polynomial. And then there are some problems that are NP-hard that are in NP, and those are NP. Those are the terms that are more familiar, P and NP. Those are decision problems, so just yes, no questions. Sharp P is basically the same as that. So sharp P hard is, you can think of it as just being NP hard, but it's a counting problem rather than a decision problem. So the result is that computing the volume of a convex polytope is sharp P hard, which means at least as hard as the hardest problems in NP, which means it needs exponential time, which means in general, even just a body defined by linear equations, you cannot compute its volume in any practical length of time in high dimensions. Okay, so hopefully that's clear. But it would be fair to ask what any of this has to do with networks. This is the network seminar, and I said I was talking about networks. So let me talk about how I actually got interested in these problems. Yeah, sort of biographically where I'm coming from. So a few years ago, I started thinking carefully about how to compare growing network models to data. So probably anyone who's read any network paper has come across some growing network models. The simplest one is probably uniform attachment. So in this, nodes just arrive one after another and attach randomly to whatever network is already there. Maybe slightly more famous is preferential attachment. Crisis model or Barabashi-Albert model being famous or well-known examples of preferential attachment models. One of my favorite is the redirection model, the Krapivsky-Redner redirection model. And so in this model, nodes come along, they pick a node at random, and they attach to a neighbor of that node rather than that node itself. And in the, I guess, the late 90s and early 2000s, these were like all the rage. Everyone was writing loads about these. There's literally hundreds or thousands of papers on it. There's so many different models in this class, but they're usually considered in the forward direction. So most of those papers, a lot of it in the physics literature, is if I follow these rules and generate a network from this model, what are the properties of those networks? So what's the degree distribution? How long are the shortest paths? What are the spectral properties of these things? Which is fine. It's a fun game we can play. You define a model and you solve some problems with the model, but it doesn't directly tell you anything about the world. It's really just a math game. And what you really want to do is you really want to compare the real world, compare data to these models. So if this is a useful model of something, then it should be something that we can look at real data and learn something about that data using this model. So what we really have is an inverse problem. We don't want to ask what are the properties of the networks that are generated by this model. We want to ask what are the properties of this data that make it more or less like this model. So this is a kind of central or standard problem in statistics, which is really just how to compare a distribution to data. And in this case, in principle, we know the distribution. I've defined a set of rules, and those rules define some probability distribution over networks. So if G is a network, then P of G is whatever distribution my model says it is, according to those rules. So for uniform attachment, the simplest case, which I'll just focus on for now, the procedure that you run if you were to sort of actually implement this in computer code is first you have a bag of nodes, you fix some order in which they're going to be introduced into the network, and then you introduce them in order and just attach them uniformly at random to what's already there. So if I had the nodes A, B, C, I could fix in order B, A, C, and then I could grow it in this way. It has to start with B, then A comes along, it has to attach to B, there's nowhere else. C comes along and then attaches to B. And so at each step of this process, I can track the probability of this move being the move that was made. So if this was my simulation, I can give that a probability. So the first thing is just the probability of fixing that order, which is 1/3 factorial. There are a factorial number of ways of ordering of things. And then given that I introduce a node in the order BAC, I can then ask what's the probability that this exact growth process occurred. I'm showing all of this for the directed case because it's simpler to discuss. So in this case, in this order, B has to come first, that's probability 1. A has to connect to B, there's nowhere else for it to connect, probability 1. And then C comes along and could have chosen either B or A to connect to. In this case, it chose B, and that gives you probability 1/2. So you multiply this whole thing out and get 1/12. That is the distribution for observing this exact sequence of steps in the simulation. But what you would actually get when you, if you run this code, almost certainly what it gives you at the end is just a network. Or another way of saying is if you actually looked at real data, it doesn't tell you, oh, well, this was introduced in exactly this way and then connected in this way. You have a network. So what you need to compare is you need to actually compute the probability of ending up here, regardless of where you started or what way you went in between. So if we use pi to denote orderings or permutations, then formally this is still an easy problem. You just have to sum over all the orderings. We don't know what the orderings or the growth process was, but sum them all out and then get the probability of the network at the end, final network. So these things are quite simple for uniform attachment. So each possible order we just assume is equally likely, 1/n factorial. So we can plug that in. For uniform attachment, the probability of a given network, given an ordering, turns out to be 1/n minus 1 factorial. If that ordering is consistent with the network and it's 0 otherwise. So a consistent ordering, just to be clear, if we have this little graph at the top, ABC, then BAC is a consistent ordering because there is this sort of history that starts at B, then A attaches, C attaches, and you end up at that network. And you never break any of the rules. That's a perfectly possible trajectory in the uniform attachment model. Another one could have been BCA, just symmetric really. So B, then C attaches, and A attaches. So those are both consistent. An inconsistent history or inconsistent ordering would be ACB. So if I had initially said I'm going to introduce the nodes in order ACB, I could never have grown this network. You can kind of try and picture it. So first A has to come and C comes, but somehow C doesn't attach to A, even though it's supposed to attach to the graph. And then B comes, and then suddenly A and C attach to B. Like it just doesn't follow the rules of the model, so it's inconsistent. So for uniform attachment, it's particularly simple, this probability of G. It's just the number of consistent histories. Once you put these two things into that sum, it's just the number of histories divided by n factorial and minus 1 factorial. And so to estimate or to evaluate P of G, all you need to do is count the number of consistent histories. So just go through every single order in which the thing could have grown and just say how many of these are consistent with the network, and then it's uniform over those things. So this actually turned out to be a well-studied problem in computer science in a very different name, which is called counting linear extensions of partial orders. So what does that mean? A total order is an ordering. just a normal idea. So in this case, B less than A less than C, that would be a total order. A partial order is like an order. There's some ordering relationship, except it's not necessarily the case that every pair of objects can be compared to each other. So you know, with this B less than A less than C, we can also, by transitivity, say that C is less than B. So all pairs of objects can be compared. But if I just give you these two relations and say B is less than A and B is less than C, you don't know whether A is greater than C or less than C. And these things just map onto graphs. So I have these arrows here. If you erase those edges and just thought of those as less than symbols rather than arrows, then this partial order in this network are structurally equivalent. And then a linear extension is just any total ordering that is consistent with the constraints of partial order. This is just saying what I was calling consistent histories is now a linear extension. It's a complete ordering of all the nodes so that none of the arrows are pointing the wrong way, or equivalently, so that this is an order in which this network could have grown, this directed network. So that's good. There's a lot of algorithms for doing this. This is a very, very well-studied problem. The bad thing is that it's known to be sharply complete, which is one of these complexity classes, which means it takes exponential time in order to do this. So even the simplest growing network model, where things just come along and attach, is very, very possibly needs exponential time to actually compare to data. In other words, these models are extremely difficult to reliably analyze statistically, unless you already know the exact order in how it grew. There are quite a lot of other problems that have this form, where there is some latent ordering or some ordering of events or some way in which something grew, but you can't observe it. Or maybe there's some optimization problem where you're trying to find the best possible order in which you could do things. So you've got scheduling problems, contact trace networks. You have partial information about who infected whom and when, but all you really have is who tested positive and when and where were they. You don't actually know demonstrably who infected whom. So you have to analyze these things in a similar way where you're dealing with a lot of unknown ordering and temporal problems. Ranking in sports, user preferences, all have this kind of flavor where you just have partial information about what's better than what or what's earlier than what, but you don't know the full thing. So all I've said really is that this is an extremely hard problem and I haven't actually helped. So what I actually want to do, or what I want to talk to you about, is how we can actually make progress solving these problems in practical scenarios, even though we believe in general this is sort of an intractable problem. So conceptually, I want to do the same thing with the triangles and move to thinking about a stochastic model or a probabilistic model where we give now each node a uniform random variable between 0 and 1. So there's some vector x. And then that vector can be mapped onto a permutation, onto an ordering. So if I give you some vector of real numbers, you can just sort those, sort the components, and that corresponds to an order. So just an example, if your random vector was 0.5, 0.2, 0.7, that would map onto the order 2, 1, 3. The smallest thing is 0.2 in the second place, and 0.5 in the first place, and 0.7 in the third place. And this is obviously a many-to-one mapping. If I just add 0.1 to uniformly to all the components, then it doesn't change anything. And in fact, each one of these, the region in X that corresponds to any given order is just those simplicities that I was talking about at the start. So This is just the region in the unit hypercube where, say, the largest element is second, so it's, and then the medium element is first, and the third element is the, well, I got that backwards, but you see what I'm saying. So each one of these orders has this 1 over n factorial volume inside the unit hypercube. And if I play this game where I give everyone a random number between 0 and 1, and just ask, once I do this and map this onto a permutation, is this permutation consistent, or does it obey all of the inequality constraints? Or equivalently, I'm asking, if I sort of throw a dart into the unit hypercube, what is the probability that I land inside some region, and this region is defined as the region that obeys all of the inequalities? What I'm trying to do is compute the volume of the polytope in high dimensions, and this particular polytope is defined so that its volume is just the number of linear extensions over n factorial. So it's the number of ways in which I can obey all of the constraints divided by the number of different orders I could have in total. So this still doesn't help solve the problem, but it's just a conceptual reimagining of the same problem. But now we're in a situation where we can start turning this into a physics problem. So instead of just saying that the xi's were completely uniformly chosen, let's define some dynamic system where these xi's are considered as spins, like an easy model. So it's some dynamic variable that can vary between 0 and 1, but there are some energetic constraints. So if node I and node j are connected in this direction with an edge like this, then the energy can take two values. If xi is less than xj, so we sort of, the directionality agrees with the edge, then that costs you no energy. And if the spins are such that it disagrees with that ordering, then that costs you 1 unit of energy. And then you can define a Gibbs distribution. So this just is a standard physics approach, but you just say that the probability of any state is proportional to e to the minus beta times the energy of the full system. And the thing on the bottom there is called the partition function, z of beta. And that is just the thing that makes sure this whole thing integrates to 1. It's supposed to be a probability distribution. So it better be the case that the whole thing integrates to 1. So you just integrate the top, put it on the bottom, and then the whole thing necessarily integrates to 1. And then what I really care about is what happens at 0 temperature. So physicists use beta, which is like the inverse of temperature, instead of temperature. So what I care about is when beta goes to infinity, what happens to this distribution? And each of the terms in this is e to the minus beta. If you've got these two, just looking at this xi and xj, then the limit of this, when you plug in that thing at the top, is either 1 or 0. So it's 1 if it obeys the constraint, and 0 if it doesn't. So it's the opposite, really, of what the energy was doing. And so this is something when you consider the product over all of the edges, all of the constraints, things that look like this. This is just saying, if the x's are such that every single constraint is met, then the probability is proportional to 1. And if the x's are such that even one of the constraints is broken, the probability is 0 of that state. So this is the uniform distribution over x's that obey all of the edge directions. And the thing there, z, is just the integral of 1 over the region where all the constraints are met. So in this case, that means that the the zero temperature or the beta goes to infinity limit of the partition function is the volume of this polytope that we defined, which is the number of linear extensions over n factorial. So at zero temperature, this physical system has a partition function that is the thing we want. Although we know that computing this thing is sharply complete. So we know that computing this partition function cannot be done in general in better than exponential time. So this still hasn't actually solved the problem. I've just shown you yet another way of looking at it.
Can I just ask, how does this relate to spring rank? This thing that's used to order.
So spring rank has a different Hamiltonian, and the Hamiltonian in spring rank is quadratic in the distance between them. So it's basically like a normal distribution. So that is Hamiltonian that's chosen so that you can efficiently make inferences about things. But that Hamiltonian doesn't have this, it doesn't have the growing network interpretation. It's just a, a different Hamiltonian.
We also have a question from the chat.
Yep.
Is computing the number of linear extension sharply complete even when we restrict to trees rather than general Gaussians?
Yeah, no, it's not. It's not. For trees, it's in P. It's it can be done fairly straightforwardly. And the examples I was showing were trees. So in those cases, it can be done fairly straightforwardly. It's general networks with loops that cause problems.
Sorry, just another question.
Yeah.
It's well understood like where this boundary is, like, because I guess there's one loop. It's sort of.
I think one loop is also doable in one time. Yeah.
Is it like well understood? Like where is this like boundary between from P to C?
I don't know. Yeah. Maybe.
Because it's all, I mean, I guess it's always about infinite size things. So
Well,
complexity.
yeah, I suppose. I mean, this is it's the scaling rather than the size limit. It's asking how it changes as n passes. Yeah. So this is a general thing. These proofs are almost always done in the worst case.
Yeah.
So instead of asking in a typical case how long would it take to do this, they're saying in the absolute worst case. So how you prove these things is you dream up some particularly nasty counterexample and then show how you can map this onto I mean, it's not necessarily nasty, but how you can map this problem onto a more general computation problem that is known to already be in the class sharp P or whatever it happens to be. So the typical case, I don't know how well that's studied, but I'm kind of getting to that in a minute. What happens in the typical case? Yeah. Any more questions? Okay. So now I am going to assume that the network is a tree, which is a case where it can be done fairly straightforwardly, but I'm not going to do a normal computer science thing of, well, we have a tree, so we can just run recursion and other things like that. But I'm going to do a physics trick where I factorize this distribution. So I have this distribution over spin states, and I'm claiming that if the network were a tree, then this distribution over spin states would have this this form. So at the top, it's a product over edges of a function of the spins at each end of that edge. And the bottom, it's product over nodes, and it's a function of the spin at that node. And in particular, these mu I, j, and the mu I. So the top one is in this whole system, what would the marginal distribution be if I just looked at these two spins that are connected to an edge and ignored everything else? And at the bottom, we're saying, if I ignore everything except for one spin, what would that spin's marginal distribution be? And then di is the degree. So this is a very general formula that can be proved by induction, but I'm not going to do that. You'll kind of have to trust me that this is true. But I can show you an example to kind of motivate where this is coming from, why this would be true. So we consider this simple case with 4 random variables, A, B, C, and D. And what I want to write down is this is some abstract distribution, but I want to write down the joint probability of A, B, C, and D. And what this network structure means is kind of showing the dependencies. So I can start writing down P of A. And then if I knew A, then I could write P of B given A. And then now I know B, I can write P of C given B and P of D given B. So the fact that this thing can be written like this is more or less the meaning of those edges. That's what that network means. And then all I need to do is now expand those conditional probabilities using the definition of conditional probability. So the probability of B given A is just the probability of A and B divided by the probability of A. I do the same for each of these. And now I can cancel these probabilities of A. And what I end up with is this equation. And now if you compare this to what we have up there, you have a term in here for every edge. So you've got P of AB, P of BC, and P of BD. So each of the 3 edges is on the top. And on the bottom, you also have a term for every node, but raised to its degree -1. So A, B, and C are degree 1. So 1 minus 1 is 0. So those terms basically cancel. And then B has degree 3. So we have P of B to the power 2. So this formula exactly agrees with the one on top. And in principle, for arbitrary trees, you can derive that this is indeed true by induction. If it's true, assuming that it's true, then obviously we can take the log of it. So logs are nice, they turn products into sums. So nothing fancy going on here, just taking the logarithm. The entropy is defined to be the negative of the expected value of the logarithm. So because expected values or expectation is linear, and this is a sum, the expectation of a sum is the sum of the expectations. And so when I do this sort of entropy thing, I can just think of this as now a sum over the entropies of these 2-point distributions, and then a sum over the entropies of the 1-point marginals. And so the entropy has to have this form where this Sij is the entropy of mu ij. You can do the same thing for the energy. So the definition of the energy is somewhat similar. It's the expected value of a sum. You can do the same thing by taking the sum of the expected values, and this is fairly straightforward. And so what this is saying is, if I knew the 2-point marginal and the 1-point marginal, then I could compute the entropy and I could compute the energy, if I knew those 2-point and 1-point marginals. And then I can use this thermodynamic relation, which just says that the partition function is the exponential of the difference of those things. So what this is saying is, if I knew the 1- and 2-point marginals, then I could compute the energy and the entropy, and then I could compute the partition function, and then I would know the number of linear extensions. So if I could proceed through this whole procedure, then I would be able to compute the thing that's difficult to compute and that I want to compute, which is the number of linear extensions or the number of consistent histories and how this network grew. So how do you get those 1- and 2-point distributions? So those distributions are also hard to compute. And in fact, you can show that in general, even computing the 1-point distribution, so that this, the probability the spin at node I takes value xi for a general network with general topology, this is also a problem that is sharply complete. So computing these things is also hard. So I'm just pushing the problem further and further and further back. I'm not actually making progress. But by following this procedure, we are making conceptual progress because now we can start bringing tools, because these are very, very common kinds of problems that arise in the physics of disordered systems. And I mean, computer scientists also do this, but belief propagation is an algorithm that is designed to approximate marginal distributions in networks that look like this. So what I'm going to do is I'm going to talk about how we can use belief propagation, use that to approximate the marginal distributions, put that into our formula for the energy and entropy, then compute the partition function, then we have the number of linear extensions. So this is also known as the cavity method. And what I want is this distribution, mu I of xi, the probability that the spin at node I has the value xi. I'm not going to compute that. First, I'm going to think about a different problem. I'm going to imagine that I remove I from the system entirely. So I started out with something like this, I is connected to these other nodes. And I'm going to consider a modified system where I just has been deleted. It's no longer there. And what I'm going to ask is, what is, in this modified system, what would the distribution of spin J be in that modified system? If I knew that, then I wouldn't just know, if I knew that for all of the neighbors, then I would know the joint distribution of all of the neighbors. Because once I remove I, these things are disconnected. So that means they're statistically independent. So I just have to multiply the distributions together. So this product over the neighbors of I is what is the joint distribution of all of the spins in the modified system. I don't actually care about the modified system. What I care about is the original problem. But if I knew what they were doing in the modified system, and I know how I interact with all of its neighbors, I can now bring I back in, knowing what they would be doing without I, and then I can integrate over that, what the neighbors would have been doing anyway, and sort of bias them to where they sort of should be by introducing I. So it's a little bit of a, it's not a very instructive formula necessarily, but this formula says this is what the distribution of the spin at node I would be in relation to what in the modified system the neighbors would be doing. And I write proportional because this thing has to be normalized. It's a distribution, so I just have to add in a constant there. So I integrate this thing to be, so it integrates 1. Okay, so I'm still just pushing the problem back further and further back because I don't know what these modified distributions are. But this is finally where you can kind of close the loop in on itself recursively. So I'm saying if I knew the modified distributions, then I would know the distribution I want. But the modified distributions, I can make the exact same kind of argument and say, well, the modified distribution at J would be like what it would look like in terms of another modified system where J is also removed. And so if you work that through, you have this equation here on the bottom, which is now there's only one kind of variable in it. This is a large system of equations, but it's the closed system of equations. There's nothing else I need to add to this. So if I can solve these equations numerically, then I can, at the bottom, then I can plug that into the thing above it. Then I can compute the entropy and the energy. Then I can compute the partition function and so on. And in fact, you can solve these equations. You just put them in the computer and let it run, and it reaches the fixed point, and you're done. You also get the 2 points from them as well. There are some technicalities in how you actually solve these things and implement it in a computer. It's not super interesting. So all of that assumed that the network was a tree. When I started it, this factorization is only true on a tree. So now the trick is to say, what if we apply the exact same algorithm to a network that is not a tree, and will it give the right answers? So I have some evidence that it does. This is a very common trick in physics, and there are reasons to believe that this algorithm does give correct or almost correct, although not exactly correct. And in particular, that full set of equations probably takes something like n log n time. So it's a good polynomial. It's not just polynomial time, it's a good polynomial. So in principle, this thing scales to extremely large things. And one could argue that it should give something like a constant error. So it's not exactly correct, but as a fraction of the, that it's a vanishingly small error. So how can I conjecture this? Why do I believe this to be true? So I can test this on simple cases. So if you start with an Erdős-Rényi graph and then direct every edge just so that it obeys the ordering on the natural numbers. And then I want to compute that thing Z through that whole tower of procedures. And that thing is a number of linear extensions divided by n factorial. The nice thing about the Erdős-Rényi graph is you can often compute things analytically. And in this case, there is an analytic formula. I mean, it doesn't really matter, but that's what it is, this thing at the bottom. And that SA is defined like this. So the expected number of linear extensions in the Erdős-Rényi graph is n factorial e to the n SA, where this thing is SA. This is all analytic, this is exact. And so now I can just run my algorithm and check that it agrees. I can simulate from the Erdős-Rényi graph, run my algorithm to count the number of extensions, check the expectations match. So that doesn't actually quite work. There's a slight complication, which is that the typical value of the number of linear extensions is concentrated away from the mean. And so actually the thing that's more relevant, if you only run, if you run 1 million simulations, you'll see 1 million typical values and you won't see something that actually looks like a mean. In an exponentially vanishing number of cases, you get something that's way, way, way out that skews the mean. So what you actually want is a slightly different quantity, but you can compute that too with the same arguments. So I've called these SA and SQ. And so here I am comparing simulations to analytic predictions. So the dotted line is and the solid line are two analytic predictions. So in this case, these two things, the expected value of the logarithm and the logarithm of the expected value. And then the crosses are measuring that and actually simulating from the model and checking. And it's quite a lot harder to measure one of these quantities. The quantity that's larger is a lot harder to estimate. That's the thing that is vanishingly rare to actually observe anything that looks like that. But this seems hopeful that the simulations agree with the theoretical predictions. So now on to something that's actually maybe more interesting, which is growing networks again. So if I started with this network A in the panel A, and ignore the colors, let's just say I gave you that network, and I told you this was generated from preferential attachment, and I asked you, use your algorithm and how accurate are those marginal distributions that this belief propagation algorithm approximated. And we said that that algorithm was exact on a tree, and it's not exact, and this is very definitely not a tree, so it certainly shouldn't be exact. But this is a small enough network that it's only 10 nodes, that I can do the full sum over 10 factorial things relatively easily. I mean, 12 factorial already starts to get hard, but 10 factorial I can do. So I can actually do the exponentially hard calculation in this case and compare it to what I'm seeing from the belief propagation. And when you compare the results for the averages of those distributions, well, we've got a correlation coefficient there of 1 for all intents and purposes. And if I look at the full distribution, so this is the marginal distribution of a few of these nodes selected randomly, and I'm comparing the exact solution with the approximate solution. And there are some little differences, but it's very, very, very small. And this is good reason to believe that this algorithm correctly or almost correctly makes inferences about growing networks. So that's all validation. But this class of problem is a fairly generic class where you have some notion of comparisons between things, but there's a lot of uncertainty. And maybe a more or a different example, but a more real world example is trying to rank things, for instance, chess players or tennis players, where the data that you have is who beat whom in some matchup. So this is kind of like the growing network example, where you have nodes, which would be players, and edges indicate who beat whom. In this case, the edges don't deterministically say, the direction of the edges isn't deterministic in who's the better player. So some of the time, sport and chess and everything would be boring if it was never the case that sort of a weaker player won. If there was no randomness, it would sort of just be, well, you know who's going to win, it's deterministic. So if we assume there is some underlying distribution of abilities, we expect some number of upsets, and then a model just tells you what is the distribution of upsets. So when should upsets occur, with what frequency? And two popular models for this. Model 1 just says upsets occur with some fixed probability, less than a half, because more often than not, better player should win, but some probability. Another model, which is actually more popular, it's sometimes called BTL model, Bradley-Terry model. And in this model, you say you have two players, they have some ability, xi and xj, and it's a logistic function, so the probability of the better player winning increases as the distance, as the difference in their abilities increases. So if I'm way better than someone else, I'm much more likely to beat them. And if we're very close, that probability approaches 50-50. Model 2 is generally preferred. It's the one that people use more frequently, and it makes a lot more sense. It's kind of obvious. If I play tennis against Roger Federer, it's like probability 0 that I can win. Whereas if he plays, someone equally or close, then that probably gets much closer to a half. But it's an empirical question. Which of these two models is better supported by the data? And why this is the same class of problems as the ones I was talking about earlier is you have some directed network, you have some ordering on the nodes that's latent that you can't observe. You have to sum over all of those things and evaluate the total probability of each model. So this was, I applied this to tennis data. So this is only the top tennis players, but it was 10 years of data of the top 500 tennis players. And it turns out that model 1 is more strongly supported in 9 of the 10 years, even though that is the model that seems intuitively not the right model or something wrong with it. This obviously would be wrong if you had every single tennis player, not even every single human in the world. Obviously, it wouldn't be a constant probability of upset, but probably when you restrict to only the top tennis players, the probability of number 10 beating number 20 and the probability of number 10 beating number 100 is like roughly similar. And there's some kind of fixed probability that the better player screws something up, has a bad day, makes too many faults. And this kind of calculation, actually validating which of these models is preferred, is again one of these problems that's sharply complete. And so by using this technique, I'm saying it's preferred, but it's only an approximation. But given the other validations, then I believe this approximation is extremely good. And I believe this is a correct result if you were to do the full exponentially difficult calculation. So yeah, that's what I've got. So just going back over things. If you want to compare data to a seemingly simple network model, just like uniform attachment, it turns out that it's extremely hard to actually do this exactly. And there are lots of these models that we've been thinking about as network scientists are very closely related to classic problems that have been studied, at least in detail, at least back to the 70s. And I don't think these connections are really appreciated. Another connection is that we can use the physics of disordered systems to derive approximations and to get algorithms that actually do this in practical scenarios. Just to come back to the question about worst case and average case, essentially these physics approximations should be sort of exact in the average case. So they should work in the average case or the typical case, but not in the worst case. And in some sense, the typical case is kind of like the random graph. Like if I give you a typical, an average network, it looks like a random graph. So this is maybe one way of coming at this problem as a physicist rather than a computer scientist and saying, sure, it's bad in the worst case, but in a typical case, we can do much, much better. So yeah, thanks to my collaborators. And these are the two main papers that cover the stuff I've been talking about today. Thanks.
Thank you, George. Do we have any questions either from the room or the Zoom chat? No, there's just one question.
Yeah, first, thanks for a great talk. So I know there's some literature as well, like approximating volumes of convex bodies. And I also know like often these are also sort of dynamical systems they run and then average out and things. So I was wondering, could that be like an alternative method, or is it even maybe equivalent in a certain sense?
Yeah, so well, in a sense it's equivalent because it's two systems that are trying to approximate the same thing. So the standard algorithms like that, they essentially amount to the same thing. They work as like a random walk inside this space, and then use that sampling to approximate the volume. And if you actually run that spin model I defined in a simulation, you'd probably do it as like a random walk. You would say, pick this spin, try and change it, pick this spin, try and change it.
Yeah.
So in a sense, those two things are different ways of looking at the same sort of simulation. The difference is this is analytic. So I don't actually run any simulations. I just write down a set of equations and then solve them. The downside is that I can't actually bound the error rigorously, or I can't improve it. It is what it is. Those simulations will give you the correct answer. And you can rigorously say, if I run this for long enough, I would get within epsilon. But the time you have to run them is a lot longer. They're a lot more expensive. And they're not analytic, they're just simulations.
Yes.
Yeah, thanks a lot. Do you have some intuition of why the approximation works?
So the standard intuition or argument is that over long, if this thing were a tree, it would be correct. And over long cycles, long cycles shouldn't really matter because the correlation as you go around the cycle sort of die off exponentially. So a tree with a few long cycles should be fine.
Locally tree like.
Yeah. Why in practice it works on networks that have many short cycles is slightly more. Just happens to, as far as I can tell. You can, there is some, actually I haven't tried, but often you can get inequality, so you can say that this is definitely less than or greater than the thing I want in certain circumstances. I don't know whether that would be true in this case, whether the bound is rigorous or whether the error could go either way. I'm not sure.
Right. If we don't have any question, Zoom maybe. Right. So thank again then. And see you next week.